Here is a puzzle. The wave equation says wave speed equals frequency of the wave times the wavelength. Doesn't it look like speed is directly proportional to frequency? And if you increase frequency, then you increase the wave speed? Let's look and see how accurate this really is. Here I've got some waves traveling on the string. I'm going to increase the frequency, and the question for you is, does that increase the speed? When I increase the frequency, do the waves travel faster? Clearly not. These crests go just as fast as the big crest. And if we do it again, these highly frequent waves do not catch up to the less frequent waves on the right. They all travel at the same speed. You can follow them moving across, and they move at the same speed. So what we just saw is that the speed of a wave is constant. Pick any one medium you like. Maybe you're talking about water waves. Maybe you're talking about waves on a string. Maybe the medium is a slinky. All of the waves in that one medium will be the same in speed. In fact, the only thing speed depends on is how quickly particles can transfer force to one another. If we go back to the simulation, if I pull this thing up, the first particle pulls on its neighbor, which pulls on its neighbor, and there's this kind of chain reaction. And I pull down, and they pull down on each other in succession. If I change the medium and increase the tension, then now when I pull this guy up, it transfers the force to the neighbor much quicker. And when I pull down, it transfers the force much quicker. So that's how you speed up the wave. You increase how quickly they can interact. Wave speed does not depend on frequency. It does not depend on wavelength. So what was my mistake up here? What did I do wrong? I made a crucial mistake. When I went from the equation to the proportionality, I took away wavelength. And so I assumed it was constant, which is absolutely not true. This was wrong. When I look at these three things, c, frequency, and lambda, what's the constant? It's the wave speed. So if you want to write a proportionality, it would be 1 is proportional to frequency times lambda, or if you divide both sides by lambda, frequency is inversely proportional to the wavelength. So before we do any problems, I have a puzzle for you. Here's a wave in green. Try and draw a wave that has twice the amplitude and half the wavelength. Well, amplitude is how high the wave is, so I need this new wave to go 2 times as high and 2 times as low. Wavelength is how long the wave is, like from one point to the next point in phase. Or you could think of it as the distance between the crests. Instead of this distance, I need the wavelength to be half of that. So I need it to be this length. One wave fits right there. So then the next wave will fit in that space, the next wave will fit there. Okay, let's try this out. Twice the height, half the length. Well, this isn't great, but you get the idea. Now let's solve 6 together. In 3.8 seconds, 2.5 cycles of a wave pass by a point. So this is the number of cycles that pass, and here's how long it takes. This is not period, because period would be the time for one cycle. What is it? Some random time delta t. In that same random time, the wave travels a distance of 1.9 meters. Just like before, this is not wavelength, because it's not the distance of one cycle. This is some random distance d. Amplitude, 0.62. Calculate the frequency of the wave. Well, frequency is defined as the number of cycles that pass per unit time, so that definition leads us to the equation. 2.5 cycles pass in 3.8 seconds. And this comes to 0.66 if we round. 1 over a second is a hertz. To find the wave speed, we can't use this formula because we're looking for speed, but we don't know wavelength. So instead, we're going to use speed is distance over time. Now I'm going to apply this not to a particle, I'm going to apply it to the wave itself. And the wave has some speed c. So the wave travels a distance of 1.9. That's like the crests are traveling that distance. How long does it take? 3.8 seconds. And this is exactly 0.50. For period, we know that it is the inverse of frequency. They are reciprocals of each other. So we're going to do 1 over and use the unrounded value. I think it's something like 657. And when you calculate the answer, you get 1.52. But for sig figs, we'll make it 1.5. Calculate the wavelength. Well, now we can use this formula. This is the only formula with wavelength. We know c, we know frequency. Speed, again, is 0.5. Frequency we know from above. It's that unrounded value, 0.6, I believe it's 657. And when you calculate lambda, this I believe is 0.76, or was it 0.67? 0.76. That's the distance of the wave, so it's measured in meters. It's the length of one cycle. Calculate the average speed of the particles. Now here's the thing, we already used this equation. And we said, let's use it for the wave itself. So this became the wave speed. But now we're going to apply it to the particle. And we know the particles travel 4 amplitudes in one period. Right, because here's a particle at the top, here's the center line, it goes down 1 amplitude, down another amplitude, up, and then another amplitude to where it began. So the wave travels across, but the particles go up and down. So we can plug in the amplitude of 0.62. The period we have from above, we use the unrounded value, and this is going to be 1.6. So look at that. On average, the particles are going way faster. They're going way faster than the crests. See that? It's like this. You've got some kind of wave where the particles are going up and down much faster and the crests are traveling across much slower.